โอเคเปิดอันนี้นะครับใช่ไหมครับอ๋อใช่เนาะโอเคครับผมปกติอาจารย์เขาให้พูดภาษาอะไรครับเห็นมีคนต้องเป็นภาษาอังกฤษมีเขียนอีเมลมาบอกว่าขอลาเป็นคนพม่าคนไหนครับคนนี้Are you from Myanmar right and should our lecture be held in English or you cannot understand Thai นะ Okay everything should be in English right okay I should I should provide everything in English too because we have an international student right okay okay today is the first day for our class right EGEL501 and I just created the classroom was just created last night this one and I don't know whether all of you would like to join into this Google Classroom or not. I'm going to give you all the detail. I don't know how to this one, right? It's course code. Sorry for that. It's in German. I'm going to zoom it for you a moment. Yeah. It's also. Moment. It's better to. But yeah. But I don't have any line contact from you, or is there anybody who has a line account with me? I'm not sure whether we can use only this letter or not. EGEL501 One of the things is that I just recorded our whole class in the mobile phone. And afterward, it's going to be uploaded to YouTube. If you fall asleep or you pay attention to something else during the course, or the class, you can repeat it in YouTube, okay? Just type our lecture code EGEL501 or 501, okay, in YouTube. It's going to be open in public, okay? But it was also available, I think, from the last year, but the link is secret somehow. I don't know, you want to publish our lecture today in YouTube or not, or is your private? But most of the time, the camera cannot see your face, okay? They just capture only your backside. So don't worry about your privacy. Is it okay to get into this course by using this, or if any of you has my line contact, just give. Okay. Then it's better. I'm gonna copy this link to you, okay, and then you can spread it. You can spread it to your friends, to your classmates. Okay, soda, right? Soda, like this. And then you can spread this link to everyone in this class. So today is the first lecture, and that's why I say first lecture in 11.08, which is August this year. All relevant books are provided in this panel, and there are two dedicated files for us. The chapter 0, which is introduction, and the first chapter. I'm not sure whether you want to start our real lecture today or not, but if you get bored or it's too hard for you to prepare your brain, then we can skip the first lecture. It's up to you. But to not waste our time, we're going to start the first chapter immediately. And I got the course syllabus from former lecturers. Actually, this course was just held for the second time here in this year. Last year was the first time. You can ask your senior, your former colleagues in the last year. I think they are 4 or 5 people, right? You can ask them about this course. Anyway, after that, you can find 4 related books here, okay? But we don't use all of the material in these 4 books, okay? But it's good if you have time and read it. I'm not sure whether you are gonna need the detail in this subject or not, but because most of you may work in electronic or in power engineering, right? I'm not sure. The content in this chapter, in this subject, will be relevant to your research area or not. Okay. Let's start the first file, which is introduction to this subject. As far as I know, this year EGEL501 still doesn't need to do or has nothing to do with grade, right? They are gonna be classified into 2 main categories, right? Pass or fail, right? But most of the time, I would give you pass score, okay? All of you will get pass score. except that you don't pay attention at all to this subject. But that never happened. Okay, the zero chapter is introduction. And formally, my name is Bambrung Thausis Kun. I work here, I think I have worked here for a couple of years, 2 or 3 years. And yeah, today is August 11, and tomorrow is going to be the holiday, right? In Thailand, it's Thai Mother Day, right? So the content in this introduction to EGEL 501 is that we need to talk about course participation, but it's not serious because you are in graduate level, right? But in bachelor degree, I'm gonna need to check one by one so that there is formative score for 10 points, okay? And it's gonna be taken from this part, which is course attention or course participation. Well, if you fall asleep or you have a special mini project from your supervisor and you have many things to do, you are busy, you may not pay attention to what I say during each lecture, but after that, you can get back home and lay down on bed or work on your private area and watch the clip, okay, the video clip that is going to be uploaded to YouTube, so you can repeat it privately in your private area. And it's going to be the introduction about me, course instructor, and this is what is missing because also last year I cannot get the name of all of you, but because this subject doesn't need the examination, right? There will be no examination as far as I know. It's going to be recognized as pass or fail, right? There is no course prerequisite, but sorry. Did you graduate from here, from Mahidol University, or you just get bachelor? Huh? From KMUTT. Okay. Welcome to Mahidol University. I think the location is not so different. It's not far from your accommodation, right? The place you stay. Okay. So I think there would be no big difference in background. So course prerequisites has nothing to do with us. The course content, okay, the detail that we are going to see in this subject, and course evaluation, there's nothing to do with this subject as well because there is no A, B, C, D grade. And textbooks are what I have already provided to Google Classroom. You can read anything as you want. But actually, some contents in those books are what you have seen during your bachelor degree level, right? Okay, not 15 sessions because we have only 13 times. I think we will face with one holiday, official holiday. That's why I think we lose one lecture day. And on the 5th lecture, I'm going to be out of our class because the department allocate me or assign me to another subject, which is for bachelor degree EGEL501. It's about basic engineering skill for the bachelor degree. So I'm sorry for that, and I need to be absent from our classroom. Okay, I need to let you know first. No, it's not 13 to 16. It's 9 to 12, right? But last year it was held from 13 to 16. It will be changed, okay? It will be corrected, and the room is not EE meeting room anymore. Last year we have 4 people, and it was held in EE meeting. It's like a casual way of lecture, but this year is more official. We have more master degree students. How many of you right now? 20, 24, 2, 4, 6, 8, 10, 12, 14, 15, right? Not 20. But you are 18 people. But right now, why? I can see only 15, or 3 of you maybe may get stuck with traffic jam or something like that, right? No problem, actually. You have YouTube, you can watch it later. Yeah, this is the first lecture day, August 11th. We lose 2 times of the lecture because one, I'm going to be absent, and we lose the last week, right? But anyway, if you, some of you really get busy with any task from your, they just come, the remaining just arrived. If you have something really serious to do, or you need to meet the deadline, like paper submission, just tell me, and we could skip like last week, okay? It's very flexible, okay? It's up to you. Yeah, you can count it. It's around 13 or 12 times for the lecture. And of course, the lecture will be uploaded for you to review the material in YouTube, okay? I have nothing to do with YouTube. I don't want to gain any income from YouTube. And the number of views in YouTube is less than 100, okay? It's not like a million views or something like that. There is no money or income from YouTube. I just upload it for you to be convenient, to follow the material from this subject. This is also done for every subject that I have. I hold here in Mahidol University, and also for bachelor degree students. And this is the official picture from the university. If you have a private question, when you don't understand at all what I say during this class, you can come to me or make an appointment in room 514. Okay, this floor, but in the first building. Please let me know first what time you want to see me. And this is the whole calendar for teaching in this semester. I need to give the lecture on Tuesday. Oh, sorry for that. The information here is in Thai. Can you understand a bit of basic word of Thai? Sorry for that. The secretary of department just gave me the schedule in Thai. I don't know why this semester she didn't send me the English version. But anyway, you would understand. This is Monday, Tuesday, Wednesday, and Thursday, Friday, right? I need to give lecture for bachelor degree in mechanical engineering department. afternoon today, every Tuesday. Okay, and this is the time dedicated to you here at EGEL 501. Okay, and that's it. Okay, you are not allowed to see me, okay, in the afternoon of each Tuesday because I need to give the lecture to bachelor degree student. Other than that, you can make an appointment, and the missing thing is the list of your name. Maybe I'm gonna need to assign some special problems that during our lecture, like I may ask you to file a research paper in IEEE Explore to track or to gain some information that corresponds to the mathematics that we're going to see in this subject. Okay. Last year it was really serious because I gave our student the work that is really like a research paper, and yeah, it was submitted. Most of them were rejected and need to be revised, but still I didn't have time to go ahead with that. There is no course prerequisite. Course prerequisite means any subject that you need to pass because this is the first year for you in master degree level, so there is no course prerequisite. But anyway, I assume that everyone at least get at least D doc grade, right, from mathematics in bachelor degree. Is there any other student who didn't get the bachelor degree from Mahidol University? Anyone from other university? No, all of you are from this department, right, from Mahidol University. This is the official detail of this subject, EGEL501. Okay, it would be comfortable to you because they provide both languages. Sorry for that. How many years have you stayed in Thailand? 2 years, 4 years, bachelor degree, right? So you would be able to understand somehow Thai languages, right? A little bit, but I don't understand you. You get you attend the international program, right, in KMUTT. So all the lectures were given in English, so it's hard for you to practice the Thai language. Okay, anyway, no problem. This page is provided in 2 languages, Thai and English. You can easily gain the information. Well, we will start with advanced algebra, which is the first chapter here in today. If we have time, we can start it. When you enter the Google Classroom, you can download this file. The lecture may contain many people, okay, they are great mathematicians during our journey in this chapter, okay. And I'm gonna bring you the impression about the people who discover some stuff in mathematics. Maybe it can give you inspiration. You may be the great mathematician in the future. Okay, so it's also convincing. Okay, where is that? This one, right? Okay, advanced algebra and functions of complex variable will be held in the first lecture here. Other topics are ordinary differential equation. Actually, this is what you have already seen, right? Eigenfunction, but without S, I think it's wrong. It's taken from EE curriculum book. and boundary condition, Green's function. This, I think you have seen this kind of thing in during your bachelor degree, right? Integral equation, approximation, Laplace equation, and Poisson equation. I don't know why they allocate these kind of topics to this subject, and maybe you may use it if you work in power engineering, right? I don't know. Wave equation, vector field, vector space. Vector space is what we may be familiar with in numerical analysis, which is very useful. Well, you can write a paper when you know only numerical analysis. That's sufficient. But I don't know. Is there any of you who may need to know Laplace equation, Poisson equation, or in your research? I don't know. For me personally, I have never used this kind of thing during my work. Okay. Okay. We go further. So the lecture for this subject will be classified into each different topic like this. Okay. I'm gonna give you a dedicated file separately later. Like advanced algebra, the same thing like in that paragraph, function of complex variable, ordinary differential equation, eigenfunction. Well, if you know well each topic, I think it's sufficient for you to create a research paper. But I don't know the requirements of your master thesis. I think the thing that you need to do during your master degree is that you have to get a conference paper, right? At least one conference paper, right? Okay. It's not difficult, and you're gonna get experience to attend a big meeting with international, with many people from around the world, and you have to give the lecture like 12 minutes and 3 minutes for question when they are interested in your work and they want to ask you. Okay, it doesn't mean that you have to know well every topic. I would say only one topic that will be sufficient for you to create a research paper. Or even you don't understand one of them at all, you can still have a chance to create the research paper. Anyway, this subject will give you fundamental knowledge so that you can read a research paper in IEEE Explore easily. Okay, I would try to. There is no course evaluation because we will give you only pass and fail credit. And the fundamental book would be this one. Okay, I think most of you may know well. It's Advanced Engineering Mathematics from Erwin Krzyk. And I would say this is the book that my teacher during my age in bachelor degree also used it at that time. So it's a classic book. When you are work in master thesis, you may need to get more idea in numerical methods, and you can go to this book. And actually, there are many books that talks about numerical techniques. Okay, but this is only an example for that. And I don't know. I cannot remember his full name. Chante, okay, lecturer Te, Ajahn Te. What is his name? His full name? Yeah. Lecturer Patranat would recommend me to give you about to give you the basic idea about writing the proof, because your work will be rigorous, will be firmly believable if you provide the appendix or at the end of each paper about the detail you get that result in mathematics, and that's called proof, right? Okay. If you are interested in that kind of thing, you may consult this book. And that's it for the chapter 0. Would you think we would be done for today's lecture, or should we start the first lecture as well? Okay, to not waste our time, because I think one of you may spend so much time. If you live in Bangkok, you may have to spend so much time and effort to arrive here, right? So to not waste your effort and time, we will start the first chapter right now. It's called Advanced Algebra. It contains many topics, like we start with vector, matrix, and I think this kind of thing would be easy for you. You have seen, but at the end of this chapter, maybe something new to you as well. Okay. It has 98 pages, quite long. If we cannot complete it in a single lecture for today, we're gonna continue it later next time. Okay. The first one is vector. I think this is the basic word you know since you were like in high school, right? You may hear these words since you were in high school. Vector. Of course, in physics, vector would be a quantity that has both magnitude, the length, and direction, right? Which is described by the arrow, right? If you have negative sign in front of that vector, it means we have to reverse the direction of that vector. For example, this is plus v, and if you have the negative one, it means actually that you multiply -1 to this one, and that's why we get the opposite direction to the arrow, and that's called -v. Okay, this is the basic thing. And if you have like a scaling factor, for example, in this one, we have number 2. It means we have the same vector, but the length is just duplicated. Okay, is twice, okay, of the original length of that vector. And if you have another vector, is for example, we say vector W, it may have different direction like this. Okay, so this is physical vector that you have seen mainly in physics. Later on, you can see this kind of vector in, I don't know, in electromagnetic wave or something like that, right? Subject, in the subject of electromagnetic wave, right? But that's the three-dimensional vector, okay, that can be described by 3 coefficients, okay, along x-axis, y-axis, and z-axis, right? It's three-dimensional Cartesian coordinate, right? And to be easily understandable, most people would have unit vector, which is mostly represented by unit vector I, unit vector j, and unit vector k, right? Yeah, along the x, y, and z axis, respectively. Well, of course, the vector along the x-axis would contain only the first coefficient, for example, a, comma 0, 0. And in this figure, the magenta vector here has the length of 0.4 in the positive way. So we have 0.4, comma 0, 0, like this, okay? And in the y component, it's going to be written as 0, comma b, comma 0, and 0, comma 0, 0.7, and comma 0, right? And in the z component, 0, 0, and c, right? And for example, in this one, it just stops at 0.6, and that's why it's written as 0, comma 0, and 0.6. So if we combine all these three separate components, we're going to get the basic thing that you may have seen during your high school, AI plus BJ and CK, right? And you can leave each coefficient to ABC location, right? So this is boring because you have seen quite often in the first year in bachelor degree. But in linear algebra, we would not pay attention to the direction because the vector in linear algebra may contain more than 3 components, ijk. And if you start from the basic vector like in high school, you can capture or write the coefficient ai, bj, and ck simply in another form, right? Like this, right? By using the bracket or parentheses. It's up to you. But in the whole lecture here in this subject, I'm going to use the square bracket like this, okay? And in the three-dimensional Cartesian coordinate system, we can write this physical vector in the bracket form like this, okay? A, B, C, like this. And of course, there are only 3 components along x, y, and z axis, right? But more generally, in linear algebra, we may have more than 3 components. Let's say n, okay? N is an integer, right? For example, n equal to 10, you're going to have 10 components, which may not be conceptualizable by brain. Can you create 10-dimensional space in your brain? It's impossible, right? Except that you are a daughter or the son of Albert Einstein, okay? You may create in your brain, but for me, I cannot do that. If you, for normal people, you can understand easily, right? Conceptualize the 3-dimensional space along x, y, and z or c. Well, for n-dimensional, you don't have to think about the visualization of this n vector anymore. Just say it's a group of numbers in the vertical alignments like this, okay? So these may be called column vector, okay? And okay, I need to tell you that this is the bold symbol font, okay? And this is the normal font without stress font, okay? When we use lowercase ภาษาไทยเรียกว่าพิมพ์เล็ก okay นะครับ lowercase bold symbol font is going to be called vector, okay? We use this kind of thing to represent vector. You may get confused. The teacher, we usually use the arrow above a variable to represent a vector. Okay, that's the way in physics. But in linear algebra, we're going to use the bold-faced font. Okay, ภาษาไทย in Thai it's called ตัวเข้มโอเคไหมครับตัวเข้มเรียกว่า vector โอเคเนาะ Okay. We use lower case font ตัวพิมพ์เล็กโอเคครับตัวเข้มพิมพ์เล็ก in Thai sorry for that we use lower case font with bold-faced style to represent vector because it may be I may follow the tradition from the guy in linear algebra. If you know a professor from MIT, you know MIT, right? Massachusetts Institute of Technology. The most widely accepted book, oh, where is the pen? By Professor Gilbert Strang. If I remember his name properly, okay, he is a professor from Massachusetts Institute of Technology. I don't know him personally. I know him. I don't know him personally. I know him by reading his book. Okay, I don't know him personally, and he doesn't know me as well. Okay, you can look for his book. Okay. In internet, linear algebra or something like that. Okay. They're going to use lower. They're going to use lower case and normal as scalar. Scalar quantity. You know, in this subject, we're going to have 3 or 4 types of quantity. 3 or 4 kind of quantities. The first one is scalar. Scalar like number 1, 2, 3, 1.5 or something like that. Okay, scalar. And the second type is lowercase. Sorry for that, my handwriting is bad. Lowercase and bold-faced. It's going to be called vector, like this. Okay. You can use any letter A, B, C, D, but for example, vector stands for, V stands for vectors. That's why I use an example like V here. And I think you have passed one of my subjects, right? You may get familiar with this kind of thing, right? Okay. He just passed the EGEL501 right? Microwave engineering or something like that. Yeah, you may be familiar with this kind of thing. And uppercase and bold-faced symbol, bold-faced style is called matrix. You know the difference between matrix, vector, and scalar, right? Scalar means you have Number 2, number 3, or 1.5, or minus 1.5. Okay, this is called scalar, right? And vector is somehow what you have seen in that slide. For example, 1, 2, minus 4. So this is called vector, right? And matrix is what you may have seen in bachelor degree, like 1, 2, minus 6, and 0, 3, 5. Okay, this is called matrix, right? Yeah. And if you say scalar, you can say C equal to 2, right? This is scalar. And if you say this is a vector, for example, what is your name? Huh? So let's say vector T. We're gonna use the boldface style of font. Okay, T equal to like this, not like this. This is the normal style. Okay, but when you have the thicker style, when you write thicker font, it's gonna be called boldface case, right? Boldface style. And if you have this matrix, it's gonna be uppercase and T, like this. Okay, this is the convention in writing or differentiate scalar, vector, and matrix. Okay, you can see it later if you scroll down these lecture notes. Okay, to let you understand realizable first, and back to your question, why we don't use the arrow, right, on top of each variable. I don't know exactly, but maybe for Gilbert Stein, Professor Gilbert Stein, he may want to write something in a simple way, because if you use the arrow above the vector, above a letter, how you create a matrix? How do you create the matrix style for this kind of thing? You may want to use uppercase with arrow to represent matrix, or what do you think? I don't know. Yeah, and Professor Gilbert Strong used this kind of thing. Okay, uses this, just implement this kind of thing, and it's not only for linear algebra society. If you read a paper from IEEE transaction on, it's a kind of IEEE journal, right? I read IEEE transaction on many things in my field in wireless communications. They're gonna follow this kind of thing, okay, this kind of table. I'm not sure when you work in power engineering or electronic or power electronics, the people somehow try to use also this convention, right? Just go to IEEE Explore. Now the people start to follow this kind of thing. Okay, we end without boldface font will be the element of that vector. Okay, for simplicity, if you write V with boldface font to represent a vector, you may use the same kind of variable with subscript. Okay, and each subscript represents the index in that vector. And when you go to, when you read a research paper and they may not write something like this, okay, because this full representation requires so much space, and typically, if you submit a paper to a conference paper or even a journal paper, they have a limitation in number of pages. Okay, you cannot submit a research work for 100 pages. Okay, they will not allow you to do that, except for very, very rare journal or publisher. Usually, they're gonna allow you only 8 pages or 10 pages to publish your work. But if you really cannot reduce your paper to satisfy or to meet those requirements like 8 pages or 10 pages, the exceeding number of pages, the exceeding pages, will cost you some money. Okay, you have to pay, like, if I remember properly, $135 per page. You can convert it to Thai baht. I don't know how much is. Sorry for that. เท่าไหร่ครับ135 US dollar เท่าไหร่ครับyeah, around 4,000 Thai baht per page. If the transaction or the journal say we allow you to, we have limitation of 8 pages, and you really cannot reduce your work because you have this kind of thing that consumes so much space, right? It takes a lot of space. You show all the details. You cannot shrink your work. You cannot reduce the number of pages, and you may have to pay your money from your wallet, okay? And the people would not use that, okay? They're gonna use some compressed version or short version like this. They're gonna say, we is a member of R with the power of N, okay? This is short, professional, and that will save you money in your paper, okay? You can also write it, okay? If you are rich, you are millionaire, and you are from a rich family, you can write it, but usually we will not do that, okay? But I just want to let you know that we come from the background like this, okay? The detail like this. Even you can write it with multiplication sign in number 1 to strictly say that vector V is a column vector, okay? And what happens if I say V is a member of R1 times N? What does that mean? Yeah, correct. Thank you very much. It's a row column, right? It's a row vector, right? This is column vector, right? You have like a bar, like a condominium, right? You know condominium, right? You live in Thailand. You may stay in a tall building, in a high, tall building dormitory. It's like condominium, right? It's a column vector, but I don't know this kind of thing. It's a vector that has this kind of shape, okay? Or single floor, but the building contains many rooms, okay? It's a row vector, right? This is the row vector. Okay, row vector, and this one is known as column vector, right? You have to differentiate it and memorize for the first time. Because if you lose this lecture, if you don't pay attention, if you go to the next lecture, you're gonna get confused. You cannot go ahead anymore. Okay, we have column and row vector for the first time. Okay, if you place n first here, it's going to be flipped as the column vector, right? This type of thing. Okay, that's the basis, right? Is the real value set, right? But in electrical engineering, we are special, like in physics society. So many quantities in electrical engineering and in physics as well, not only in our area. In electrical engineering, we have something like phasors, right? The quantity that is complex value, right? So it's a complex number. So the set may not be easy like a real number set for us at all. It's going to be complex. Okay. So of course, the vector can be drawn from a complex number like the real case. And if you want to precisely represent the column, oh, sorry for that. This is not metric. อันนี้ผิดนะครับ เดี๋ยวผมไปแก้ให้ It's vector. It is wrong. I will correct it later. This is typo. Okay, vector. Sorry for that. When the vector is strict column vector, you can write it multiplied by 1. Okay. Sorry for that. I'm gonna change it. Vectors can be represented in two styles, right? Row vectors and column vector, as you know. A row vector will be written like this. Okay, it has a single row and many columns, right? You know, this one in this way, right? The horizontal way is called row, right? And the way downward like this is called column, right? I don't know, in Thai we call this is Thai word. Tail, right? Tail. And in Burmese, what is the name of row? I would like to learn also. Row. What is the word row in your language? Huh? There. Okay. And column, what is the word in Burma? In Myanmar? Huh? Tao. Okay. Just for the first time to get to know this. When I get a chance to present the paper, I'm going to say these two words in the conference in Myanmar. Okay. Yeah. Row and column, number of column like this. Okay. If you have a single row, we're going to call it row vector. If you have a single column, it's going to be called column vector. All right. Explicit example for row vectors are like this. Vector 1, vector 2, the first vector, the second vector, and the third vector. When your set are integer, it's going to be -7, 3, 0, or 0, -5, 4, -2. This is integer set, right? I don't know how to write it. Right? The integer set like this, right? And for real set like this, our elements will be drawn from, it can be also negative, right? -7 point, blah, blah, blah. This is the real value. You can see it in like MATLAB, right? Everybody knows MATLAB, right? Get to know MATLAB. Or, I don't know, maybe you may be familiar with, you may get used to octave, you know, octave. Octave in English, sorry, octave is the pronunciation in German. Octave is the clone is the free version of MATLAB. You can write it octave in Google search engine. It's a free version, because I did my PhD from Germany, and most German people do not use the illegal software. They will not install the illegal license of MATLAB in their laptop or computer. So they try to hold this rule by avoiding the illegal version or illegal license of MATLAB by using Octave, which is the clone version of MATLAB. Many instructions of Octave and MATLAB are very, very similar, but not 100%. But maybe you are in the new generation people, and you may be familiar with Python, right? Python. Do you use Python? Okay, very good. It's more modern languages, computer languages. Yeah, the result in MATLAB or Python would give you something like this in the real electrical engineering problem. Okay, it will not give you the result like this. I just showed this one for you to get the basic or easy background in the concept of row vector. Okay, but if you type it in Octave or MATLAB or Python, you will get the result like this. But this is also the simple case, because usually in our work in EE problem, in electrical engineering problem, we would face with complex style of problem, right? Because when you work in power distribution problem, for example, our voltages will be represented in phasor form, right? And the phasor quantity is actually a complex number, right? So you will get the value in complex like this, which has the real part and the imaginary part, right? The number that stay behind I, right? Please try to not be confused. This I is different from I in what you have seen here. Okay, this I is different. I here is the unit vector along the x-axis, right? And this I is not the unit vector anymore. What is that? What is this I? It's unit imaginary number, right? I is square root minus 1, right? It's called imaginary unit, right? The first, the basis of the upper axis in the complex plane, right? Can you remember that plane, the complex plane? You have im, right? And you have real, right? For example, if your z is 3 plus I4, it means you have to go along these 3 steps, right? And you have to go up by 4, right? And your z will be this, right? This is z. Okay, yeah, I is the unit scale along the imaginary axis, okay? This is I, okay? It's not the same I as you have seen here in the 3-dimensional Cartesian space. You have ijk, but with arrow, okay? It's different. Even it has the same letter I, but different meaning. Okay, now let's move to column vector. You have a single column like this, but with multiple rows, with many rows. Example of column vector is like this. Okay, if you come from high school, you're gonna get integer 7 minus 4 minus 1 minus 9, but when you really work in your bachelor degree thesis or your senior project work, right? And you write it in computer program, you're gonna get a result like this. Especially you are in electrical engineering, you will get complex quantity as well, the imaginary part. Oh, I get confused. What is the size of this vector? What is the size of this vector? Is it which is correct? Can you tell me, please? A, that one has the shape of 1 by 1. 2 by 1. C, 3 by 1. Oh, sorry for that. 1 by 2. D, 3 by 1. And E, 1 by 3. What is the size of V5? Which choice is correct? A, B, C, D. ตอบอันไหนถูก Which one? 3 by 1. Is that correct? No, I don't think. It's 3 by 2. It's a matrix or vector. I get confused. Matrix or vector? Vector of size 3 by 1. Oh, very good. You can pass this subject already. You don't get confused. That's very good. We have 3 elements, 3 entries. For those who are quiet, what do you think? It's very easy, teacher. I can count it myself in my head. We have 3 entries or 3 elements, right? This is the first one, the second one, and the third element, right? They are allocated in a vertical way, right? And it doesn't mean that you say you have 1, 2, 3, 4, 5, 6 elements. No. They have positive or plus sign together with the I here. It means this is only a single element, okay, but it's complex number, okay. Don't get confused when you write the code in MATLAB or Python and you get try or you didn't have enough food in your stomach, and you can get confused. And you may say, oh, your program is wrong because it gives you the result of 3 by 2. No, it's not 3 by 2, it's 3 by 1. Okay, but the result is complex. That's why it's a column vector, actually. Okay, this is an example of the result from what you may face with in reality in electrical engineering. Okay, let's move to another. What is this person? Paul Dirac. Have you ever heard his name before? In physics, I think, in your high school, you may see he writes something, I don't know what about his formula in the blackboard. You know, in that generation, also in my generation, we use blackboard, but in your generation, it's more modern, they use whiteboard like this. What about the students in Myanmar? You use the green board like that, or you have whiteboard here in Myanmar? This is modern, very cool. Are you from capital of Myanmar or another city? Capital? Huh? Yangon. Oh, very cool. So it's modern. During my primary school, like 30 years ago, I was grown up in a school that where my teachers wrote everything in the ancient blackboard like this. Okay. Yeah, the reason why Paul Dirac stand in front of this kind of thing because he was in 1984. Okay, it was quite old. You may hear his name from quantum mechanics. And what is the reason why we have to get to know him in this subject? Because in quantum mechanics, even you, I need to explain you first. Even you are in electrical engineering, now every work, the research work now has many disciplines, okay? You may see some works from the people, especially in Europe. I have most of my experience were about Europe. Okay, European researchers would do something about quantum mechanics. Even you are in electrical engineering, many people work on quantum mechanics as well. And when you may get a chance to read the papers from those people, and when they work on quantum mechanics, they use this kind of notation to represent a column vector. They use a straight vertical bar and the angle symbol to cover a letter like this, boldface font and lowercase letter to represent a column vector. And they flip the arrow of that vector, and they flip the location. They swap the location of the straight vertical line and the arrow, and it's going to be row vector with this star. What is that star? Star is complex conjugate. Everybody gets to know complex conjugate, right? Like if you have 3 plus I4 star, it means you have 3 minus I4, right? And that's called complex conjugate. And that's the same kind of thing here, star, okay? So they are from physics societies, a bit different from us, from electrical engineering, but it's quite understandable, right, for you if you read a paper from the physics people in physics society, for example, in quantum mechanics. Right? Even you get this lecture in electrical engineering, I would suppose that you are supposed to be able to read the paper in physics, in quantum mechanics as well, because they share the same principle like this. And one of the major operators is transpose, right, to change or like its name suggested, the transpose means it transfer the column vector to row vector, or to change the number of row and columns in a matrix. Okay, and it converts a row vector into column vector. It converts column vector into a row vector. For example, if you have a row vector like this, and when you do the transpose for that, you're going to get a column vector, right? This is the basic thing. I need to refresh your story, right? You may get used to this before, right? You have learned it before. If you have a column vector like this, and when we have a transpose, it becomes a low vector immediately. Now let's move to the basic linear algebra, matrix multiplication and inner product. Matrix multiplication, okay. Example of transpose, if you have the row vector with integer inside, you will get a column vector, and you have nothing to do with that, okay? Just change the direction of the allocation. And even you have the real space, you just flip the location from horizontal way to the vertical way, like this. And it holds the same principle also for the complex domain. If you have a row complex vector like this, when you make a transport, you're going to get the column vector. And here is another example. And if you have like many more multidimensional, more dimensions, you use the same principle, okay, from column vector to row vector, and from column to row vector. The font size here is smaller because I don't want to cut it to another line. To represent it in a single line would be easier for you to see how it's going. Now let's move to the third one, which is matrix. Okay. Matrix is an extended version of vectors. If you have good background in matrix, in vectors, you can easily get the idea of matrix. Matrix is something that collects several vectors. For example, V equal to many small v. Okay. Again, this V has I just erased it. Uppercase and boldface. Sorry for that. This is uppercase. Okay, we just delete it or remove it. Uppercase font and boldface style or stressing style. And you have like n column, right? Capital N columns. From 1 to until n. For example, if this capital N is 10, we're going to have 10 columns. And each column, each vector here is the column vector. Okay. The 3 dots mean and so on. Okay. 3 dots mean so on until the last column vector. Each element, each column element has something to do like this. Okay, it had its own sub-elements like V1, comma n, V2, comma n, V capital M, comma n, like this. So it means the height of this vector is m, and the width of this matrix is n. So it's written like this. V is a member of the complex set with m rows, the number of rows, right? Like this, right? And n columns, 1, 2, 3 until n, capital N. Okay. Are you confused already? Not yet. I hope not yet, right? If you have a scalar like k, if you multiply a vector by k, k will be distributed to every element inside that vector. K will be moved, will be transferred to each element of that vector. Okay, this is the basic thing that you have seen during your high school. The same holds also for matrix. Okay, if you multiply a matrix, let's say matrix M with element M, so many M's, right? With M by N, okay? And if you have a scalar K, scalar is like this, right? Scalar is number 2, number 3, or minus 1.5. You just distribute it to each element of that matrix as well. And you may ask me, what is the higher dimension of matrix? That will be called that will be called tensor. Okay, this word. It can have another layer of matrix. Okay, it's called tensor. I think if you type this word, if you use this word in IEEE Explorer, you will find many works, many papers about that. Okay, but we will talk about tensor later. Okay, if you have more time, if you go to doctoral degree level or PhD level, we will talk about PhD. Because now the time is limited. Okay, we will stop it at matrix. I think with matrix, you will be sufficient to write a research paper, and then you can complete your master degree, okay? But if you are really interested, you can find a time and come to me and talk about tensor later. But now the time is limited. Okay, my former classmate during PhD, during master degree, he works on image processing, and he deal with this kind of thing, tensor, during his master degree. Okay, well, when you are in my field in signal processing, you have to be fluent in mathematics, okay? But we will not be very proficient like the guy in mathematics in Faculty of Science, okay? We are not good like them, but we just apply mathematics for electrical engineering problem, okay? We need to have a bit skill in mathematics. So yeah, we will limit our attention to only matrix. You just distribute K to each element of M. Well, you don't have to worry about this concept. I just tell you how it's going. Actually, you know it from your high school. But this kind of operation will happen automatically in your programming platform like MATLAB or Octave. Okay, you need to know about that. Example of this kind of multiplication is like this. If you have a column vector, what is the size of this one? 1 by 2, 2 by 1, 2 by 2, or 4 by 2, or what? What is the size of this quantity? Huh? Sorry? 2 by 1, right? Very good. It has 2 rows and single column, right? You just distribute 3 to each row, right? 3 goes to not only -6, but also number 3 here as well, okay? You have to distribute 3 to 6 and 3, 7 and 9 as well. That's why you get the result like this, okay? If you don't believe me, just program it in MATLAB, okay? You will get the result like this. Should I show it also in MATLAB for you? No, it's gonna waste our time, right? Okay, and for matrix, because the matrix consumes so much space, I will give you a compact version of that concept by using only integer set like this. -4 will go to -7, and that's why you get positive 28, okay? Minus and to -8. This is quite boring, right? It's quite simple for you. But you need to know that -4 will go to every element in that matrix, okay? You don't have to calculate by 10, okay? Because you have computer programming skill, okay? But this kind of thing will happen for you automatically inside your code, your program, okay? I don't know, maybe you are a supervisor. If you find a supervisor, he or she may ask you to write a code to do something in his interested problem, okay, in the problem that he would like to solve. In addition and subtraction of 2 vectors, that's quite simple, right? You just combine one by one elements of the operation, like plus or minus, right? And is it, my question is the following. Is it possible to do the addition or subtraction for the vectors that has different size? Is it possible? For example, if you have the vector of like this, if you have vector A, which is 2, 1, and vector B, this is both phase time, and 0, 3, 4, is it possible to compute A plus B? Can we do that? No. If you write it in your MATLAB, they're going to say wrong operation, because the size of vector A and vector B are not the same, okay? Because this one is 2 by 1 and this is 3 by 1, right? The size are not the same. The size of these two vectors are not the same. You will get nothing. But if you get the result, it means there will be something wrong in your code, okay? Your code will be cracked, okay, immediately, okay? When you run and you hit the enter or the run button in your program. The most important thing is that you have to make sure that both vectors share the same size, okay, have the same size. And an example for you to refresh yourself, for example, 3 by 1, if you have 3 vectors, 5, 0, 0, minus 2, 0, 0, 0, 9. When you add them together, so they will appear in each entry like this, okay? You may feel sleepy because it's boring, right? What about the combination of addition and multiplication? If you have 2 in front of the first vector and minus 4 in front of the second vector and 3 in front of the third vector, you just distribute to each element, okay, to each element for these 3 vectors, and then you add them or you sum them finally, and you get the result like this, okay? 3 by 1, 3 by 1, 3 by 1. The final result should be 3 by 1. But if you write a code, a program, and you get the result 4 by 1, for example, there would be something wrong in your code, okay, in your program, okay? I don't want you to compute this kind of thing. It's boring. It's just consume your energy. Everything will be done in your CPU, in your processor, okay? But you are in master degree level. You need to know the concept that the size of each input should be the same as the output, okay? 3 by 1. And the same also for matrix. 2 matrices should share the same size or should have the same size in order to perform addition or subtraction. Okay, when you have, you need to do summation or you need to deduce something from another matrix. You have to make sure that both matrices have the same size. If your matrices do not have the same size, you're going to get cracked or stopped error or notification from MATLAB or Octave or from Python immediately. I don't know what language, what are the language that you use, you may need to use. C, yeah, C as well. Or I don't know, Turbo Pascal, or no one uses anymore, right? Or Fortran, you know Fortran? Have you? Is there anyone who heard about Fortran? No, it's from grandfather generation. Okay, Fortran. Or maybe my teacher was familiar with Fortran, but I think in our generation we need to have the skill about Python, right? That's the most common language. Okay, let's see an example for the subtraction and addition of these two matrices. Matrix A and matrix B has something like this, and if you want to perform the summation or addition, you just make the summation, the element that correspond to each other. For example, 1 by 1, it means you have to sum number 2 and number 1. Okay, 1 and 1 here, 1 and 6, right? Until you reach the final element, okay, in 2 and 1, okay, right? Will give you number 3 here, okay. And the same for deduction or subtraction. 2 minus 1 will give you number 1, right? Minus 2 minus 1, so it's plus 1 is going to be minus 1 until the last element like this. Now let's talk about the multiplication of matrix by a vector. Well, this is what you also got the experience before, right? One of the important things is that the number of columns in the first matrix should be the same number of the elements in that column vector. Okay, in this example, it has n columns, right? So the succeeding vector should have the same size, and that's called n by 1. Okay. Okay. Let me ask you, if I have if we have a vector A like this, and I have a matrix B, and we have like 3 or 6 and 9 minus 11, 14. Oh, sorry, 14. And minus 1, 7, 5. Is it possible to perform the multiplication B and A? Is it possible? Can we do that? We cannot do that, right? Because here is 3 by 3, right? And this one is 2 by 1. The number of elements, the number of rows in the succeeding or the vector here on the right side is not the same as the number of the columns in this matrix. So if you try to force the computer to do that, they will stop it. Your program is going to be cracked. Okay, it will stop immediately. You will not get nothing. But if you get the result, it means you would write something wrong in your code. Okay, usually the program will be cracked and stop it. They will give you nothing. Okay. Okay, the way to understand how the machine to get the result is this basic thing that you have learned before in your high school era. The vector, the succeeding vector, will go to the first row, the second row, and to the last row. Okay, it will perform the inner products. And what is inner product? Inner product means you multiply two vectors 1 by 1, and then make summation, right, to that thing. Another way to understand the machine is that you just leave the element from the succeeding vector to each column of that matrix, okay, and then you scale it, and then finally you make a summation of all the results. You will get the same result like this, okay, summation. And to better see the concept, okay, I just gave you an example. This is 3 by 3 and this is 3 by 1. Number 2 will go to this one, right? Number 5 will go to number 1. 0 will go to 6, like this. And then you compute the multiplication, the product, and then you find a summation to each row. You get something like this. The most important thing is that you need to realize that this is 3 by 3 and 3 by 1. So 3 by 3 and the next one is 3 by 1 will give you the result like 3 by 1, okay? And that's why you get the column vector like this, 3 by 1, okay? This is what you need to automatically recognize. And another way is that you perform the multiplication in the second way. Number 2 will stay in front of the first column. Number 5 will stay as the scaling factor to the second column. 0 will stay as the scaling factor for the third column. And then finally, after the multiplication, you make a summation. You get also the same value, which is 7 or 6, 7, the same result. Okay. And transport of the matrix is nothing, right? You just flip, you change xm1 to this location, okay? x21 to this location, and xm2 from this location to be here, right? M2. To be here, and m comma n will be also here. But the important thing is that the size will be flipped. Okay, from m by n will be n by m, right? As you see here, at the beginning you have m rows and n columns. Finally, you have n rows and m columns. Okay. Let Y be a matrix like n by p matrix. And if you want to make the transport of two matrices with standing there like a product like this, the rule is that when you try to distribute the transport operator, you have to change the sequence. You can see here, x stay in the left side, right? But when you distribute the transport operator, x will stay on the right side, and y will be on the left instead. Okay. If you don't believe this rule, I will give you an example. We have the multiplication of two matrices like A and B, which share the same side, 3 by 3. And of course, 3 by 3 and 3 by 3 would be multiplicable, right? We can multiply 3 by 3 and 3 by 3. There will be no problem, right, in size or in dimension. When you make the multiplication of these two matrices, A and B, and finally you make a transport, you change the location of 27 to be here, 31 to be here, and so on. You get something like this, right? And when you make the transport to each matrix first, okay, B need to stay on the left instead of the right, and you will get the same result, 2 minus 14 and 17 like this, okay? So this verify that the transport of A times B is equal to B transport and A transport, okay? Let's talk about the spatial structure of the matrix. This is basic thing you need to know when you go to a research paper. They may simply say symmetric matrix, right? Symmetric matrix mean your matrix is real value, okay? The element is taken from real Z, and the matrix should be a square matrix. What is the meaning of square matrix? Square matrix means the number of rows and the number of columns are the same, right? Square matrix means for example here, you have 3 by 3. The number of row is 3. Number of column is 3, right? This is called square square matrix. Oh, sorry for that. Square matrix. I think everyone knows about this, right? And another thing is like this. Another kind of matrix is like this. What is the dimension or size of this matrix? It's 4 by 2. Okay, this is 3 by 3, 4 by 2. When the number of columns or rows are not the same, this is called rectangle or rectangular matrix, right? Okay, when you read some basic books and they say square matrix, it means the number of rows and the number of columns are the same. And when they say rectangle matrix or rectangular matrix, it means the number of rows and the number of columns are not the same. Okay. The symmetric property will be held, okay, will be available when your matrix is square only. Okay. Symmetric property will not take place for rectangular matrix. No. Okay. Only for square matrix. All right. This is understandable? Okay. And another important subset of symmetric matrix is that the word orthogonal. You know, I had a colleague from Greece. I have worked with a Greek people before. She said this is taken from her language. Okay, this is taken from Greek actually. This word. That would make sense, right? Because technology or science was developed from Greek culture, right? And she said this is the word in her language. So what does that mean? It means if you make the inner product means the transpose stay inside between those two matrices. Okay, but when T stay outside those two matrices, it's gonna be called outer product. Okay, when transpose stay inside or between those two matrices, it's gonna be called inner product. Okay, the orthogonal property is that when the matrix provide the inner product as identity matrix, we will call X as orthogonal. Okay, we will call X orthogonal. What is IN? I need to refresh your background. Okay, IN is identity matrix, right? I think everyone got to know before. Identity matrix start from 2, not 1. Okay, for example, I2 is equal to number one, and 0, 0, right? This is the basic thing from your high school, right? Sorry, where is, okay, here. And I3, what do you imagine? What do you think? I3 will be 1, 1, 1, right? And 0, 0, 0, right? Like this. Okay? And what about I4? Oh, it's boring. The lecturer, the teacher. The size will be explored, will be expanded to 4 columns and 4 rows, right? But it has the same concept. This direction is called, oh, here, they provide the pen here. Okay. This is called diagonal, right? Okay, you have to leave number 1 along the diagonal, and the number of elements will be the one that stay as a subscript here of I, okay? You have 4 times of 1, okay? And the other part will be here as, will appear here as 0, right? Okay, I4. And IN means everyone on the diagonal will be number 1, right? And the other or the remaining elements will be 0. So this is orthogonal. Why do you need to know or hear these words? Because when you go to a research paper in I3 Explore, they simply say this transfer matrix is orthogonal. So you can easily see this kind of thing that could happen in research paper. They just simply say orthogonal property, okay, in their work. I need to give you the basic idea. Orthogonal means when they make the inner product, you're going to get identity matrix like this, okay. Oh, it's hard to understand. Maybe I would provide you an example. Now let's move to another person. Hermitian transport of matrices. If we don't have this person, we will skip this topic, okay? But unfortunately, he existed in this world, okay? He appeared before in this world. His name is Charles Hermite, I think, if I pronounce it properly. He is from France. He's a mathematician, of course. He did many things in number theory, quadratic form. I hope that when I have the age like him, my head will not be like him, like this, okay? I would be more handsome. I would expect so. Okay, maybe he is on the age of 60. Now I'm 40, blah, blah, blah. Maybe I will follow him. Okay, yeah. He talked about orthogonal polynomials and elliptic function and algebra. That's why we need to know him. Please remember his name, Hermite. The word Hermitian is derived from his surname. Okay, what is your surname? Yeah, if you create anything in mathematics, the people will take your surname to be one of the operator in linear algebra. Okay, please create anything that is new, that is not discovered yet in the world. Okay, and they will use your surname to represent in algebra. What is Hermitian transport? Hermitian transport is simply the transport, but with an additional operator, and that's not difficult for us. It's star, which is complex conjugate. So let me make conclusion. The Hermitian transport uses letter H, okay, for simplicity. Other people may use different style of thing. They may simply use, I don't know, this notation, this one as well in computer. But for this lecture, I simply used H to represent his name, right? His surname, actually. Well, yeah, Hermitian is the operator that includes both transpose and complex conjugate. Okay, we do both. And you would like to ask me, what happens if our data, our matrix, is real? In that case, if X contains only real number, Hermitian transpose will be the same as normal transpose, okay? Because we have nothing to do with complex conjugate. The complex conjugate of real number is nothing, right? For example, 2 star is equal to 2. We have nothing to do with number 2, right? For the complex conjugate on the real number. And of course, for matrix, if you have XH, it will be simply XT, okay? XH equal to XT, which is a transpose, okay? When X is real, M by N, okay? This will hold true. But when when your matrix doesn't contain only real number, it has also imaginary part, or simply speaking, it is a complex matrix. You have to perform also the complex conjugate. And what is the reason why we need to deal with the Hermitian transpose? Because we are in electrical engineering, right? And we have to deal with the data that is complex. So that's why we have to get to know the idea or concept of Hermitian transpose. Well, if you have 3 matrices standing together like this, oh my God, is there any chance for us to face with, to encounter this problem? Assume that if you work in my research area in wireless communications or in signal processing, we have sometimes 6 matrices staying together, okay? So 3 matrices are the simple case for us, okay? I'll represent only the simple case for us. So just follow the former technique, okay? When you have real, when you have the 2 matrices, the right will go to the left and the left will go to the right when you do the separate transpose to each matrix. Okay, just follow this idea to the 3 matrices case. Okay, for example, if you have X, Y, and Z, move matrix Z or matrix C to the left, Y will stay in the middle, so we have nothing to change. And X from left to right, like this, okay? It's not difficult, right? And one of the property that you may be able to hear in the research paper is Hermitian property. Hermitian property is like the symmetric property. Did I show you an example of symmetric matrix? Not yet, right? Okay. So I will show you an example of symmetric matrix. For example, I2 is an example of a symmetric matrix. So when you make a transpose, you get the same thing, right? So identity matrix is an example of symmetric matrix. But if you want to really see the real example of symmetric matrix is going to be like 2 minus 3, minus 3 and 4 here. If you make the transpose to this matrix, you will get the same thing, okay? The same matrix, same result in minus 3 and 4. The reason is that the element on the off diagonals are the same, and that's why when you make the transpose, you will get the same result. But for a moment, this is the real case, right? And it's called symmetric property, right? Symmetric. But when our work, we are in electrical engineering, when our work deals with complex data, we have to perform Hermitian transpose, which includes complex conjugate. And if the result remains the same, we will call that matrix a Hermitian matrix, okay? I will give you an example like this. I'm not sure whether is there any example in the lecture notes. For example, you have 10 and 3 plus I4 and 3 minus I4. And here is number 7. And if you take the Hermitian transpose, so it means you have to do 10, 3 minus I4 and 3 plus I4 and number 7. You have to do first. So the sequence is the sequence doesn't matter. Okay, you can do anything first. For example, if you do the transpose first and then conjugate, you will get the result like this. You get the result like this. 10 and then 3 minus I4, 3 plus I4 and then 7, right? You perform transpose to this matrix, right? You have to move this one to the lower and lower left side, the lower left position, and move this one to the upper right position, right? This is the operation of transpose, right? And after that, the remaining operation is complex conjugate, right? Like this. And the final equality, oh my God, is not bright enough. The final equality will be, you have to distribute complex conjugate to each element. 10 conjugate will be 10, right? 10 with complex conjugate. And what about this? 3 plus I4. And what about this? 3 minus I4. And then, should we do anything with number 7? No, nothing happened, right? So you can see that the result will be the same as the original matrix, right? Yeah, we call this matrix the Hermitian matrix. Okay? You understand that? This one, this property, okay, it's called Hermitian matrix. You may ask me, why should I need to know about this? Because if you go to the research paper, they will simply say, our transfer matrix is Hermitian. You have to know that. You have to realize that. When you take the Hermitian operator, that matrix will be the same. Okay? I'm not sure whether you will get this kind of chance or not to face with Hermitian matrix. But at least, if you move to my research area, when the people say Hermitian matrix, you understand it immediately, right? You get the concept. Okay, if you get the proper idea about Hermitian matrix, one of my questions is the following. Let's say this is matrix A, okay, matrix A. And if I have a matrix like this, 1 minus I5 and 2 plus I3 and 2 minus I3 and then minus I7. What do you think whether I is Hermitian or not? Is matrix A a Hermitian matrix? Is it Hermitian or no? What do you think? Who think that this matrix is Hermitian? Please raise your hand. Who think that this matrix is not Hermitian? Please raise your hand. And what about the people who doesn't raise your hand, or you still doesn't, or you still get the confused with the concept of Hermitian? So the result, the answer is that this matrix is not Hermitian. Okay, it's not Hermitian. What is the reason? Why? Why we say it's not Hermitian? Because the diagonal element is complex. It has also imaginary part, but when you take the complex conjugate, you're going to change this value as well. And that's why this matrix will not be or won't be Hermitian. Okay? The Hermitian matrix would have real value on its diagonal only. Okay? Okay? You get some idea about Hermitian matrix? And that's the reason why you need to know this person. If this person was not born in our world, we don't need to learn about this stuff anymore. Okay? Yeah. We cannot avoid that. Okay. Another one is called unitary. Unitary means something like orthogonal. Orthogonal is the real case, if you can remember properly. Orthogonal is something that happens for the real case, but unitary is the orthogonal case, orthogonal property in the complex case. You get confused about that? Oh my God, I got headaches anymore right now, right? Well, unitary is like orthogonal, but it's the word for the complex case. If you look at this page, it said orthogonal because our set is real. But when our set is complex, this word is called unitary. Okay. What is the meaning of unitary? Unitary means it's like the word unit. Unit means number one, right? It means the result will be diagonal with the matrix, which has number one along diagonal direction, right? And the next word is called normal. Normal matrix means if you make the inner product, you will get the same result as outer product. Okay, and this matrix should be only square. Okay, this is the square matrix n by n. Is it square or what? Is it rectangular matrix? All right, it's like this or it's like this. Okay, this is square. Okay. Okay. Anyway, if you go to a paper, you need to read a paper when they say this transfer matrix is Hermitian, is unitary, is normal. You have to go to this page to see what is the exact property for that quantity. Okay. Okay, multiplication of two matrices is what you may have seen before, right? In bachelor degree or in high school. But what I would like to mention to you is that usually it's not like you have the product of two numbers. You have 2 by 3, which is 6, right? And you can get the same result when you change the sequence of the first and the second number. You get the same value, right, which is 6. That holds true for only scalar, but when you change the sequence in multiplication, this will usually not hold true for matrix. Okay, you won't get the same result. A times B will not be the same as B times A. It's not like this. This is true only when you work with scalar quantity, like 1, 2 by 3, and 3 by 2, like this. Okay, and what else? Okay, the example to show you this property is the following. This property, okay. Okay, when you want to derive or create a new idea, you cannot change the location of A and B. It's not like this, okay? Here you can change the location of 2 and 3, right? Without any problem, without any issue. But for matrix, you cannot change the location of the first and the second matrix. I will show you an example. This is the first matrix, which is called matrix A. This is the second matrix, which is called matrix B. For simplicity, we're going to talk about the real case and the integer member. When you perform A times B, A first and then B later, you get the result like 4, 6, 14, and blah, blah, blah. And when you try to observe the result B and A, B first and A afterwards, you get the result like minus 6, 37, and 30. You can see that even in the first row, they are not the same. Okay, so you cannot change the sequence of B and A. It will be totally different. Okay, not like this in the scalar case. Okay. Now let's move to the fourth or the third person. His name is Moore, right? He is from the U.S. He's a mathematician, Eliakim Hastings Moore. He's not quite so old, okay? He's a modern mathematician. And you can see, this is the photo in black and white, so it's a real photograph, right? Which is taken from camera, so it means that he's not so old, actually. But the people like this one looks like from hand drawing, right? This is really old. But here, these two people are taken from the real photograph, real camera. So, and even this person, I think, he is still living. Okay, he has not passed away yet. His name is Penrose. Okay, why do we need to get to know these two people? He is from England. He also received a Nobel laureate, Nobel Prize in Physics. Well, you have learned before, right? The inverse matrix, right? if A is equal to 1 and 2, and here is, let's say 0 minus 1, what is A inward? What is A inward? Moment. Can we perform inverse for rectangular matrix? We usually perform inverse to square matrix, right? Not even symmetric. We can perform to any matrix, even it's not symmetric, right? We can do inverse to square matrix. Is it correct? And can you do the inverse for this matrix? For example, B equal to 1, 3, 7, and 11, 0, 5. Can we do the find the inverse of B? You learn from your high school or even bachelor degree that the inverse of A could be found by hand. Let's say, for example, if you don't want to go to MATLAB or computation program, it's going to be 1 by determinant of A, right? And change the location, right? And 0 or minus 2, right? Oh, moment. What is the determinant of A? This one. What is the determinant of A? Determinant of A is determinant of 1, 2, 0, minus 1, right? And that's equal to 1, minus 1, and minus 0 and 2, right? So it becomes minus 1, right? And you substitute this into this, it's going to be 1, 2, 0, minus 1, right? Right? This one. So A inverse is this thing. And what is the meaning of A inverse? A inverse means if you multiply A and A inverse, you must get identity of size 2, right? Because it starts from 2 by 2, right? You're going to get something like this. Can you prove that? Can you show that A times A inverse equal to I2? Let's try on your machine, on your iPad or paper. Is this result correct? ภาษาไทยนะลองคูณให้ดูหน่อยว่าออกมาเป็น I2 หรือเปล่าทดลองหน่อยเดี๋ยวฟังอย่างเดียวแล้วเดี๋ยวไม่คิดตามนะจะได้ดึงกลับคืนมาเดี๋ยวไปต่อแล้วคุณจะตามยากเลย Can you prove that A times A inverse equal to I2? Just try it like this. 0 minus 1 and 1, 2, 0 minus 1. To check that we have properly compute the inverse of a matrix and to refresh yourself how to determine the inverse, right? is it equal to I2 or not? Is it correct? Just multiply these two matrices and show me whether it's equal to, it equals this one or not. Did you get identity matrix? Or it's wrong, or the inverse is wrong? I2, right? Is correct? Okay. Now you understand the concept of identity matrix, right? We get identity matrix. And would you please show me againกระดานก็เล็กจังเลยครับ Okay, would you please show me again A inverse and A. What is that? A inverse and A means that you have to start with 1, 2, and 0 minus 1, right? And then 1, 2, 0 minus 1, right? And what is that? Can you perform that by hand? Or even you are clever, you can use also a machine like MATLAB or Octave or Python or any programming language. Okay, I'm going to leave your time so that we arrive at the result. If you just listen to me and see this expression, you may not completely understand or get the idea. Okay. So what is the result then? It's still identity matrix, right? I2, right? So you get 1, 0, and 0, 1, right? I will go to each person whether you really get identity matrix, or you use the Octave or a MATLAB or what? Why do you get the result quite easily? Oh, okay, clever. You use technology. Okay. Okay, very good. Identity matrix, right? I2, right? We simply say I2. This is simply called I2, right? Because it has a size of 2, right? Identity matrix of size 2, right? Oh, okay, I'm waiting for you to get identity matrix. Okay, I2. So let me summarize the concept of identity matrix. It's a matrix that you multiply in the front or in the real position. You will get identity matrix. Okay, that's the property, basic property from what you have learned before in bachelor degree or even in high school. Behind or before, okay, you will get the same result, which is I2. But if you look at this property more specifically, this inverse could be found for only square matrix, right? Why we say A is square matrix? Because it has the side of 2 by 2, right? The number of rows is the same as the number of columns, right? 2. So we call square matrix. But what happens if your problem doesn't have square matrix? For example, this matrix B. Is matrix B rectangle or square? B is rectangle because it's a member of, what is the size for that? 3 by 2, right? It's rectangle. Oh my God. Oh, we don't have another color. I don't wear. Okay. Black. Because here the number of row is not the same as number of columns, so we call rectangular matrix. How could we find the inverse of A? So that we can get identity matrix like before. Can we perform normal inverse like this? No. It's beyond my knowledge right now, the teacher, right? Yeah, that's why I need to introduce you to these two people, okay? They are clever, not me, okay? I am the person who just try to bring their concept to you in this room, okay? You have to say thank you to Moore and Penrose, okay? I hope that my head will not be the same like him, okay, at the age of 60. Roger Penrose and Moore, I think, Moore, are two guys who discover the inverse of rectangular matrix independently, okay? They did the same problem without knowing each other before, and they discovered the inverse of rectangular matrices, okay? And the idea is the following. Because rectangular matrix has two cases. The first case is that the number of the number of rows is can be greater than the number of columns, right? It's like condominium, right? High, tall building, right? The number of floors is greater than the number of rooms in the vertical way, okay? It's condominium. So we have more rows than columns. That's the first case. When you have more rows like this is the condominium case, okay? Or apartment case. When you have more rows than columns, you have to follow this one. Okay? When you have more columns than rows, for example, where should I write? Somewhere here, because they don't have. You know, if you watch the lecture by MIT, they have 6 or 8 whiteboards separated. They scroll down and up, right? But here, I cannot do anything. I have to remove all the time, okay? This is the first case, right? Number of rows is greater than number of column, right? But when you have this case, let's say 10 minus 3 in 5 O and 2, 6. Here in this case, number of column is greater than number of row. When you meet this situation, you have to follow this case, okay? This way to compute the inverse. It's not the proper inverse like you have before in the square case. We are gonna say pseudo inverse. Okay, pseudo means it's not the actual inverse. It's like artificial inverse. Okay, artificial inverse. And to give the honor to the guys who discovered, we sometimes say more Penrose inverse. Okay, to give the honor to those persons. Okay, those people. But if you discover something new like Hermite, Hermitian, or Moore and Penrose, they're gonna say your name as well to be the operator in linear algebra. Okay, please discover a new thing in linear algebra. I'm gonna be proud because I was one of your lecturer, your teacher before. Okay, but for me, I have not discovered something new yet. I just use what they say in the past. Okay, this is the first case. The second case, more rows than column, more columns than row. Then you have to follow the first case and the lower case, the upper and the lower case. Okay, you cannot swap it. It's going to be wrong. Okay, and when you compute it. What happens if you compute the pseudo inverse for square matrix? Is it possible? It's possible. Okay, you can do it, but you will spend so much effort. Okay, you will pay so much burden to that computation, because this will give you identity matrix. And finally, the pseudo inverse will be the normal inverse when your metric is square, okay? So actually, you don't have to do it. Just compute the normal inverse or the proper inverse. Okay, let us see the example. For example, I3 like this. I didn't have the example for you. Okay, moment. Let me show you, give you an example in internet like October online. Okay. Sorry, I didn't capture any example into the slide. You may have to look at this in this one. Okay. Do we get the result? Okay, here. Can you see it? Right here. Yeah, Octave. You can try it. octaveonline.net. Okay, it's free. Okay, let's compute the pseudo inverse of B, right? This one. Let's say, I will say both metric B equal to 1, 11, and 3, 0, right? And then 7 and 5, right? We get, right, this is result like, oh, where is that? Okay, we get the result like this. Is that correct? 1, 11, 3, 0, 7, 5, right? The way to compute pseudo-inverse, Moore-Penrose inverse is that if I remember properly, P inverse matrix B. You can simply say without BM and underscore as well, okay? You can say B, it works as well. But I want to differentiate it from the scalar B, and that's why I say both math, okay, both math, or both symbol. You can remove it, but I usually write it to recognize this is the matrix, it's not a scalar, okay? And enter it, hit the enter button, and you're gonna get result. Oh my God, like this. I cannot write it easily in by hand, okay? It contains a lot of digits after the decimal point. Yeah, the pseudo-inverse, okay? Does it correspond to the theory that I have given on the lecture note? On the lecture, we are gonna have BM, B, right, and times BM, B, and then transport, right? Transport is this one. Dot and that mean transport, the T operator, okay? Transport, this one. But if you leave only that, it's going to be Hermitian transport that deals with complex data, okay, complex metrics. Oh, sorry for that. This is, and the transport is like this, right? And -1 times BMB and dot that. Okay, that's the upper formula. Okay, upper formula means x Hermitian, x, and then inverse of the whole thing, and times x Hermitian, right? But what is the reason why I just use only transport? Why? What is the reason why I simply type transport instead of Hermitian?
Because you only have a real number.
Yeah, right. Because our B contains only real value elements, right? You can simply use transport. But if your B is complex, we have to use H or Hermitian, okay? But I can show you also the complex case, but it's going to be more difficult. It's going to be complicated, okay? For simplicity, I show you only the real case, real value case, okay? In real value case, H will become transport or T, right? T. But this is the general case for complex metrics, okay? For complex metrics. Okay, let's see the results. Oh my God, what happened? Okay, oh my God, connection lost. Oh my God, I have to, here, okay, no problem. And we're gonna hit the enter button. Oh, wrong. Maybe because I switched to another program, we have to type it again. Oh my God, we have to type it again. Moment. It's better if I switch to another program. Where is that? Madonna compiler. Okay. This one. I think Madonna. Madonna compiler. Okay. If you want to try, use this one, Madonna compiler. Madonna compiler. Okay, sorry, moment. We write it again. BMB is equal to 111 and 30 and 75, and then pseudo invert by MATLAB like this, okay, and okay, BMP by octave, okay, and BMP by lecture note, okay, by lecture note. It's going to be this is transport, right? And normal one and the inverse for all. And times BMB. Transport. Why? What's wrong? Okay, anyway, I just want to try to run. Okay. Oh, can you see it? It's quite small. Oh, I cannot zoom it. Can you see it? When you stay in the back row, can you see it clearly? Okay. Otherwise, you have to move it. I cannot zoom in this application in Madonna. Okay, 137, is that correct? 137, right? And 1105. This is the command computed by Octave or MATLAB, okay? As I told you, Octave is the clone or the free version of MATLAB. In MATLAB, you have to write your student email address, right? For entering the license, right? But Octave is free, okay? The command is nearly the same as, okay. You use PINV, right? Pseudo invert, and you get this result, okay? And this is the command in lecture note, right? As I told you, this one, the upper, okay, the upper line here, X transpose and X, and the inverse for all, and times X transpose, right? Because we are talking about the real case. And Madonna gives you this one. You can see that they share the same value, right? For every element. It means it's correct, right? The one that I told you in the lecture note is correct, all right? Which is the same as the one that you get from the program, from Octave or from MATLAB. Oh my God, where? Okay, here is the command. Okay, sorry, ข้างหลังเห็นไหมเนี่ยเห็นคำสั่งไหมครับพอเห็นนะถ้าคุณอยากลองคุณก็พิมพ์เอานะครับโอเคไหมI hope that when you stay in the the back row, you can see the command clearly. This is the command PINV, okay? It stands for pseudo inverse, which is available in MATLAB. I don't know I know in Python, but I cannot remember properly. And here is the command that is used that is shown in lecture notes, okay, to explain you how the program compute, okay. In real computation, don't use this one, okay. Use the available command in the program. Why? Because it's shorter, you can skip anything that is difficult to check, okay? Because when your code has like 1,000 lines, it's not beautiful at all to have something like this, okay? You need to use the short version of each line, right? So that you can check or to find the error or the typo easily, okay? Yeah, I show you the basic way to compute the pseudo inverse. Is there anyone who would like to see the result of this kind of thing? The Y matrix. This is the tall matrix, right? This is tall matrix. Both are rectangular matrices, right? In different cases, right? You want to see this? Okay, I'm going to show you whether the lower line here, whether this is really correct. Don't believe the teacher, okay? Is that correct? I can show you in the program as well. Okay, moment. Before we go to the second case, what is the property of Moore-Penrose inverse? You know earlier that A and A inverse is equal to I, right? And A inverse and A equal to I as well, right? And what is the property of Moore-Penrose inverse? Well, we have to talk about two cases. In the upper case, the tall matrix, you will get something like this. A M P times A equal to I. But this is true only for tall matrix. What is tall matrix? This one. This is example of tall matrix. Okay. This is Y matrix. Okay. This is a tall matrix. Okay, because the number of rows is more than the number of columns, right? So this holds true for tall matrix. If you don't believe me, I'm going to show you in the program. Okay, where is that? Madonna here. Okay. Result to show you BM, this one, right? Times BMB. Okay? If our theory is correct, what I teach you here is correct, it must be identity, right? Now let's see whether it's identity matrix or not. Do you hit the enter? Oh, more, sorry. Hey, teacher, It doesn't remain 1, 1, 0, 0. You get what? What is that? Is that identity matrix? No. Nearly. Because you have minus 1 point blah 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 e minus 16. What is e minus 16? 10 power minus 16. What is that? It's nearly 0, right? You have to count the number, the position after the decimal point, 16 location, and that's where the minus 1 located. You count the number, the position, 16 after decimal point. It's already 0, right? And you may ask me, the teacher, why it's not really 0? Right? You may ask me why. We don't get 0 as in the theory. In theory, it should be 1, 1, 0, 0, 1, right? But what you get is 1 and 10 minus 16 and 1 and something 10 minus 16, right? This is 1 times 10 minus 1 time. Why? You know that this is machine, this is CPU, this is processor, right? You may have studied, you have passed some subject about this before, right? It's something about electronics, right? You know, the computer has a finite amount of memory, right? When they keep a number, they cannot keep all the number after the decimal points, right? They can keep something like 13, 32 location after the decimal point, or 64 or something like that. Because the number is not perfect when they make the multiplication and blah, blah, blah. There is the error, there is an error, okay? And that's called, I think, if I remember properly, law of error. Okay, please Google it. There is a word about it. Law of error. It's the error due to finite amount of memory in the machine. Okay, so can you tell me which is clever between human and machine? Who is more clever? We are more clever than machine, but we don't have good ability or capability like a machine, right? When we need to deal with a lot of number, right? But from the theory, it should reach this one, right? In theory, it must be a perfect identity, but because the machine, because the machine doesn't have infinite memory, they have finite memory, right? When they keep the number into the memory, they just keep only like 32 or 64 point after the decimal point, okay? And that's why we get the round of error here. Okay, just Google it for more detail. I need to show you because otherwise you get shocked. You get the result that is different from the theory that you learn from the classroom, okay? I need to mention that this is what you can easily find when you do the real implementation of any idea, okay? Now, should we go ahead or the time is over, right? In 3 minutes. Okay, anyway, I show you this case, the Y matrix, and then we will go away, right? Moment. Where is that? Madonna. This one. Okay. Sorts. Now the next matrix is matrix C. It's 10, Fi-
Can you try to have the position of the matrix when you want to do that?
if you want to see A and AMP, right?
Yeah, because
Okay, okay.
calculated is not an identity matrix.
No, it's not identity matrix.
So it can be only this case.
Yeah, it holds true only this case. If you want to see the identity matrix for the Y matrix, you have to try this A and AMP. That will give you identity matrix for the Y matrix case, which is the lower one. The where? Come. The lower one here. Okay. This is true for the upper case. This is true for the lower case, which is Y matrix. This is true for the tall matrix. Okay, all right? I have to mention. It doesn't hold true like a square matrix or the normal inverse. Okay, you can change the sequence. And then you get I, but that will never hold true for pseudo inverse or the more Penrose inverse. Okay, I have to show you the Y case, right? 10, 5, 2, and then minus 3 and 6 like this, all right? And copy and C, right? And C, and then here from the lecture note, right? 2 version and paste. And result to show you again, right? Result to show you again. It should be C and C. And we have to move C to the first location, right? Paste. Okay? C like this, okay? C and C more Penrose. And it's different, okay? Show you and show you again. They are different quantities. Now let's see the result. Okay, here. We have C 10, 5, 2, minus 3, 0, 6, minus 3, 0, 6, right? And the pseudo inverse by octave like this. It's different. My God. Oh, no. It's wrong, right? It's wrong here. We have to move. Sorry. And I think, if I remember properly, this is minus a dash, right? And the multiplication here is let me check it again. Where? Okay. X Hamilton here. That correct? Is that correct? Okay. Run it. Okay. This is by octave, by the program itself, by using the command PINV, right? And here is from the lecture note. You can see the result is the same. And here, the way we check C and C more Penrose inverse, right? It returns exactly identity matrix. Yeah, 1, 1, and 0, 0. Okay. In some cases, you will be lucky to get the real 0. But usually, from my experience, we don't get 0 because because of the round-off effect, okay, round-off error. So I think the time is over. That's it for the lecture of today. The remain will be continue next time, okay? If you have any questions, just raise your hand, ask me, or talk to me later. Bye bye. สวัสดีครับ